Hello, in this video I'm going to start talking about collections of fundamental particles. So we've spent a reasonable amount of time on the standard model of particle physics where we were looking at fundamental particles, the things that aren't made up of any smaller particles. But of course these aggregate together. We've been talking about quarks and leptons and bosons and things like that, but that's not the world around us. These things group together in order to make the matter that we see. So how is this happening? And I'm going to do this probably in two videos because there's quite a lot to go through. So I'm going to start, first of all, getting up to the level of an atomic nucleus. And then in the next one, I'll start looking at atoms. So what is it that is allowing these particles to group together? And why do some of them group together and not others? Well, at the heart of all of this is the Pauli exclusion principle. This is one of the key ideas of quantum mechanics, and the Pauli exclusion principle, essentially that is certain particles block each other from filling up certain quantum states. Essentially they block each other and fill up space. And as we said when we were looking at the standard model, this is fermions. Fermions are the things that obey the Pauli exclusion principle. These are the things that have got half integer spin. So fermions, these were our quarks and our leptons. So it's quarks and leptons that are going to be giving us solid matter. These are the ones that we're going to be most interested in. And it's one thing for them to take up space. So this is the first thing we need, that they're taking up space because of the Pauli exclusion principle. The other thing is we need something that's going to hold them together. So we need some kind of binding force. Or a binding interaction, whichever language we're wanting to talk about. And I'm probably going to flip-flop between these because it doesn't really matter with what we're talking about here which word we're using. We're not getting into the details and the nitty-gritty of particle physics. So using the word force is fine because it makes it easier to understand certain things. This is much more descriptive. So we need things to hold stuff together. Now, we've got two forces that are good candidates for this. We've got the strong nuclear force and we've got the electromagnetic force. So these are the things that can bind stuff. Now, the strong nuclear force is the supercharged one. This is about 1,000 times stronger than the electromagnetic force. So we're going to get a lot of mileage out of the strong force, and it can overcome electromagnetic repulsion. So we can start sticking positively charged stuff or negatively charged stuff together, providing we've got some strong force there, which is giving a greater attractive force than the electromagnetic repulsion. And this is the route that we're going down with quarks. It's only quarks that experience this strong force. And they can group together in lots of different ways if you want to get into the really exotic stuff that's cooked up in particle accelerators. But we've got two quarks or three quarks. So if you've got two quarks together, which is going to be a quark and an antiquark, these are called mesons. And if you've got three quarks together, where we're going to have up, down, down, and up, up, down. These are the two that we're particularly interested in, but other permutations apply. These are baryons, and if things are just made of quarks in general, then they're called hadrons, and I'll get onto where all those words have come from in a minute. So mesons aren't particularly stable, but you can get pairs of quarks. If you've got three of them, up, down, down, that is a neutron. If you've got up, up, down, that is a proton. So the up quark has got plus two thirds, if I can write numbers properly, of the basic electric charge. Down quark has got minus 1/3 of that basic charge. So you can see here, if you've got a neutron, you've got one up and two downs, which makes it zero charge. For a proton with two ups and one down off gives us a +1 charge. So this is then allowing these two up quarks, which are both positively charged, to hang around in a proton, because the strong interaction can dominate, providing you can get them close enough together. Because the strong interaction, and I'll say more about this in another video, is only attractive, which is this bit here, is repulsive at really crazily short distances. But when you get to around about 10 to the minus 15 meters, this strong interaction is strongly attractive and will massively out muscle the electromagnetic repulsion between these up quarks inside the proton. But it does place a limit on the size of atomic nuclei, because this strong interaction is not only working inside the proton to bind these up quarks together, but then you can start grouping protons together. Providing you get them close enough. Okay, they're both positively charged, but if you can get them around 10 to the minus 15 meters apart, then they'll still hold together. But this is then placing this upper limit on how many protons you can, stick together. Neutrons are just adding even more strong force in without the electromagnetic repulsion. But the only thing holding neutrons together is going to be the strong force as well. There's no electric charge there. So they're all binding with this strong nuclear force, but there's a limit, because eventually this electromagnetic repulsion from all the protons is going to get too much. You're going to have too many protons and you start getting out of the range of the strong nuclear force. So this is how we're building these things up. In the next video, I'll then take it to the next step with atoms, because of course, if you're sticking all of these protons and neutrons together, you've now got a particle, a composite particle, because it's made up of all these fundamental particles, from quarks to protons to the atomic nucleus. But this is now positively charged, which means it can start attracting in leptons. Leptons don't get attracted with the strong force because they're not quarks. They don't engage in the strong interaction, but the electromagnetic attraction of this positive nucleus with the negative electron means we can start binding electrons in and making those atoms. And I'll talk about more about that in the next video. One thing as well to say about this, of how these protons and neutrons arrange themselves in the nucleus of an atom, is there's similarities here between the strong nuclear force and the arrangement of protons and neutrons, and the electromagnetic force and the arrangement of electrons in molecules. So how from your chemistry and such like, these electrons are existing in different energy levels, in different shells inside atoms, and we've got ways of describing all of that and how they behave, how they arrange themselves, these electrons, in molecules and in atoms. Well, you've got a similar thing described by quantum chromodynamics for how quarks inside protons and neutrons arrange themselves, and then how protons and neutrons arrange themselves inside an atomic nucleus. And you get similar sort of shell type structures that you can, at least from an analogy point of view, say is similar to the way electrons behave themselves. But it's a whole different theory describing how that behaves. But then that is a key part of the binding energy. When we start talking about how stable an atomic nucleus is because these protons and neutrons can arrange themselves in different ways. And that's why some isotopes are going to be more stable than others, because they're bound in different ways. In the same way as we see electrons want to drop down to these lower level, lower energy states inside atoms, and then they become more stable. You've got a similar thing with protons and neutrons. So we'll come back to that a bit more when we're talking about radioactivity, but it's something worth being aware of at this stage. So I think that covers everything that I want to say really about how these particles start building up, at least at this subatomic level. I'm just going to finish by saying something about the different words, because we've got quark, lepton, hadron, baryon, meson. We've got all of these things being thrown around here. So let's talk about some of these. Quark is a bit of a weird one. It's different from the others, as it hasn't come from the Greek. Most of these things come from the Greek, or they're named after people. You know, fermions, we've already said, named after Enrico Fermi. And boson, although I haven't written it down here, you know, we've had that as well, named after Bose. So quarks, though, was taken from Finnegan's Wake, which was written by James Joyce. It is, I must say, it's not my cup of tea. It is ridiculously difficult to read. I would recommend trying to read a page of it just to see how difficult it is to get a grip of what's going on. But James Joyce was an interesting character in what he was writing. But I'm no expert when it comes to literature, so I'm going to stay away from saying any more about that. But there's a line in it where you've got this 3 quarks for muster mark, whatever the hell that's meant to mean. But 3 quarks, so this is going back to the 3 here in baryons. So 3 quarks for muster mark. It was just picked up from that line as, oh well, we'll call them quarks then. I mean, it's all a bit weak for me, but there you go. That's where the name came from. So that's dealt with quarks. So let's look at some of the others. Right, hadrons. So this is one that's coming from the Greek. So hadros, if we're going to write that out in Greek. So this symbol here, if you see that above a vowel at the start of a Greek word, that's more or less saying you've got an H there. So turning that into English in inverted commas with the characters, that'd be HADR. This thing looks like a P is an R. That's our rho, OS. So hadros, which means large or massive. Not far off with what we've got here with is it Barus or Baros? I can't remember now, but let's go with Barus, which means heavy, again come from the Greek. Mesons, another one that comes from the Greek, so this is mesos. You'll see here as well just a little thing with Greek, 2 different ways of writing S's. So you've got an S if it's in the middle of a word, or not at the end of a word, essentially in a different character, but S is at the end of a word. But mesos, that means intermediate, because it's somewhere between the mass of a proton and an electron or an individual quark, whichever one you're looking at. So it's got this sort of intermediate mass. So we've got those. Lepton, so that comes from leptos, which is small or light. So again, that's come from the Greek, and yeah, leptons, they are small or light. So yeah, I think that's covered the ones that I've mentioned here as to where these words come from. But yeah, they're mainly Greek things related to their mass, certainly in this case. So yeah, I'll leave that here for now, and then I'll come back in the next one and just say a little bit about atoms, and a few things that seem a little bit weird with how they're put together.